All right, guys, just a couple little notes about atomic energy level diagrams and atomic spectroscopy. So one thing that you've probably seen before is like a model of an atom with energy levels around it, or say the electron orbitals around it. So here would represent, let's say, the nucleus of an atom, and then you'll have the lowest energy level for the electrons, which we'll call the ground state here. So this is what's called the ground state. All right, that's the lowest energy level that, say, an electron can be in. And then you can go up from that, and let's put two other levels on here. So there's one, and then there's one more. All right, and let's give these guys values. So just for the sake of argument, let's say that this energy level, this inner one here, the ground state, let's call it, it'll be minus 14 eV, just for the sake of argument. This next one will be at some higher level. So let's just call this one, we'll say it's minus 4 eV. And then finally, the outermost one that's represented here, let's say it's minus 1.5. So this outer one will be minus 1.5 eV, right? And if we put an electron in these set of levels, let's say the electron is, the atom is excited, and so the electron is out here in this outer level. Okay, so here's an electron. And we'll say it's in we'll call it in an excited state. Okay, so this part here is the nucleus, this middle part. So it kind of represents the nucleus, and then the electrons are in these little orbitals around it. So this is the nucleus here. Okay, so you got the nucleus and the levels above it. Now another way to write this, that this is represented sometimes, instead of drawing the atom, another way to write it, which I'll kind of put over here, to write the same energy level diagram for this atom, what you can do is put the lowest level kind of down here and say that this is your minus 14 eV level. Right, and then going up from that, you get to say minus 4 eV. And then we've got our minus 1.5 eV here. Okay, and so then the idea, of course, here is you could kind of think of the nucleus being down here, and you could think of the electron being free as being, I'll kind of dot it in there, but just something to think about. But the electron being free, you could think of it being at 0 eV. So the reason for the sort of the negative energies that are listed, like here and there, is the idea is that if the electron is free, an electron that's free, that's not moving, has a total energy, let's say, of 0. And then if it's bound in an atom, you've got negative energy. In other words, you'd have to give it, if you were sitting here, you'd have to give it 1.5 eV just to get the electron away, right? So what we have here is we have an electron that happens to be sitting in this state, to match what's going on in this atom. Well, so what can happen is the electron, of course, wants to fall down to lower levels, and so there's a couple ways it can do that. One thing it could do is just fall all the way down to the ground state. So that's one thing that this electron could do, is it could drop down like this. Right? Well, so this is the electron losing energy. Well, if the electron loses energy, that energy's got to go somewhere. And so where it's going to go is it's going to come off in the form of a very particular photon. So light will come off, light ray will come off. And as you might imagine, if you're going from minus 1.5 to minus 14, why, you've lost 12.5. So this thing would be a 12.5 EV photon that would come off. So that's one of the colors, or one of the light rays that can come off of this thing. We'll see later this is a UV light ray, this particular one. Another thing that this electron could do is, again, if you have it in the excited state, the other thing it could have done is it could have fallen only to this level, going from -1.5 to -4. Well, that's going to kick out a 2.5 eV photon. We'll see later. I think that turns out to be greenish yellow. So I'll kind of draw that in here this way. I'm purposefully drawing it with like a longer, lazier wavelength than this one, because it's a smaller energy and longer wavelength photon. So that's going to be 2.5 eV photon. And then that electron, after it's fallen this far, then it might fall from this next level all the way down. So the other transition that it can make once it fell there is it could complete the process by falling to the ground state the rest of the way, falling from -4 to -14. So that's going to be a 10 eV photon, looks like. So maybe I'll circle these just so so they look different from the, yeah. So you have a 10 eV photon, 12.5 eV, and a 2.5 eV. So these photons are kind of like a fingerprint of this atom, right? So in fact, I'm just going to kind of list them down here. Looks like we have a possibility of a 2.5 eV, comma 10. You could get a 10 eV photon, and you can get a 12.5 eV photon. Okay. Those same things you could see here. I guess for the heck of it, we can draw them in. Yeah, this would be your 12.5 eV transition. And then you have the other possibilities here where you fall this far, kicking off a 2.5, 2.5 eV, or falling all the way, the rest of the way down, where this is going to be like a 10 eV photon. So that's a fingerprint of this very particular atom, and so you can actually use that to identify atoms. When people talk about doing spectroscopy, like our Mars rover, it will look at the types of light that come off of materials, and from the set of light rays that come off, you can tell what it is. So final thing that's often asked, that you're often asked to do with this, is figure out actually what the wavelengths are that go along with this. And so the way that we can get those, the wavelengths that correspond to these, is for a photon. Let me get a better marker here. Energy of a photon is HF or HC over lambda. Where if you remember this HC, just to handle this with like convenient units, a very convenient relationship is that the energy of a photon is, well, HC is 1240 EV times nanometers. And what that does is it lets you convert directly from, say, EV to nanometers over the wavelength. So I guess what, if we're solving for the wavelength, we just got to divide 1240 over E. So if we do it this way, the wavelength in nanometers is going to be 1240 divided by the energy. So let's do that really quick with these three. So let's see, if this one, if you go for the 2.5 eV one, if you say 1240 divided by 2.5, that ends up getting you, and I wrote it down here somewhere, that gives you a 496 nanometer, 496 nanometer photon. That happens to be almost green. This is like green yellow. So kind of yellowish green photon. You'd see that one. This guy, if you do, this is an easier one. If you do 1240 over 10, that's going to give you a 124 nanometer photon. Not going to see that one. That one's UV. That's too short. If you remember, the shortest ones that you can see, cutoff's around 400. So that guy's going to be too short to see. And then likewise, this one, if you do 1240 over 12.5, that ends up being about, let's let's see, 99.2 nanometers nm. And so that guy is also UV. That's a UV photon. Right? So these very particular UV photons and this particular green-yellow photon would be part of the fingerprint of this atom. Okay? So that's an atomic spectrum for this atom would be these very particular wavelengths and not others. Okay? You can't have a transition that's, say, 9 eV. There's no 9 eV gap between any of these energy levels. Okay? So one more thing that we'll do with this is if you are in an excited state and kicking out the photons. One last thing we're going to look at is if you're in the ground state and you send photons in. Okay, so one other little thing on this page, and this will kind of be the last thing. Let me just erase this. Now what we're going to do is we're going to draw the same atom in its ground state and look at what happens when we shoot light in. Okay, so instead of drawing the full atom, let's just draw the sort of the energy level diagram. So let's do that here. So let's see, our very lowest one was minus 14 eV. So we're going to say that we're in the ground state. Let's put an electron in there. Then our next level was minus 4 eV. So empty level up there. We're going to say again that the atom is in the ground state. And then we're going to put a minus 1.5 eV level here too. Minus 1.5 eV. And what I want to do real quick, just because it will help you, all see how this stuff works, is let's look at what happens if you shoot in different types of light. So we'll say shoot in, let's do it this way. We'll make a little chart. We'll say the photon shot in, and then we're going to see what the effect is. Okay, and we're going to shoot in a bunch of different photons. A couple photons that we'll try. Let's try 8 eV. Let's try 10 eV. Let's try a 11 eV. Let's try 12.5 eV. And let's try 13.5 EV. Okay, and see what happens. Right, so these are the photons that we're going to try to shoot into this atom and see what happens. So let's go for this. So the very first one that we try to shoot in is this 8 eV photon. So here's the atom in the ground state, and see if we can kind of guess what happens. Well, it turns out if you try to shoot an 8 eV photon in here, nothing will happen because there is no energy level available that's 8 eV above this one in order to accept this thing. And so the effect of shooting an 8 eV photon is, we'll say nothing, exclamation point. And that's because there is no, what would you need? You would need a, a minus 6 eV. There's no minus 6 eV level to accept the electron. So what would happen is this material would basically be transparent to 8 eV photons. They would go right through. As a matter of fact, anything less than 10, which we're doing next, this thing will just let it go through. Even, watch out for a pitfall. This thing will not accept a 2.5 EV photon, even though this is a 2.5 EV gap, because there's no level that's 2.5 EV above for this electron to jump into. Okay, 10 EV you can probably guess. The electron's promoted to the minus 4 EV level. So E minus promoted to minus 4 EV. So it'll come in and it'll just lift it up. Okay. 11 EV photons. Imagine 11 EV of energy coming into this thing. Now, if it's the first time you're seeing this, somebody might think, oh, maybe there's a way to get it here and then somehow there's some left over. Again, though, it turns out nothing will happen here because there isn't what would it be, a -3 eV level. So again, it just will not accept it. It won't take the photon. So we can say nothing. And again, the issue is that there's no -3 eV level to accept the electron. I'll say exists. I'll just say it that way. Finally, we get this one. This one's probably pretty obvious. You shoot this in. Well, 12.5 eV above this one is that one. And so you'll pump that electron up into this excited state, -1.5 eV. And so what you'll get is we will promote, to -1.5 eV. Let's add one more to the list because I just see it here. Down here, let's put 14.5 eV. Let's do that. This one, 13.5. Again, you pump it in there. 13.5 would take it up to -0.5, but there's no -0.5 level. So again, this is going to be a nothing. There's no level available to take it. All right, now here's something new. We have you come in with 14.5 eV. Well, the deal is this amount of energy is what's needed to get up to the 0 eV level, which is basically freeing the electron. And so the idea is to get this thing out, you would use 14 eV to get it out, and then any extra energy it can just use or express it as kinetic. So what's going to happen here is the electron leaves the atom. You've actually given the electron enough energy to get out of the atom. So the electron leaves the atom. You've ionized the atom. So the electron leaves the atom with, and then you can see that it's going to have half an eV left over. So it's going to have 0.5 eV of Ke. Right? So again, just for funsies, like we can just kind of put, like, let's say we hit it with a 20 eV photon. Well, if you come in, 14 of it are just going to be getting out, getting to the 0 level. And then, well, if you used up 14, that means you got 6 left over. So here we can say again, the electron leaves with 6 eV of Ke. Electron leaves with 6 eV of Ke. Okay, so moral of the story, if you're trying to see what types of photons can this thing absorb, right? So this is called an absorbance spectrum. Let's look at the list of what we've done. Okay, so this is going to be our absorption, okay? What's going to happen is it will take photons at what do we got? At 10 eV. So it'll take those. So it'll take them at 10 eV. It'll take, what else did it take? It took a 12.5. 12.5 eV. So it'll take that. It'll take those two, and then it will take anything over 14. So then once you get to 14 eV, it would take anything above that. So this again, for an atom in the ground state, this would be what's called the absorption spectrum. You would shine light at it. It would take 10 eV to get there. It would take a 12.5 eV to get there, and anything over 14, the electron would take. So again, this is also a fingerprint of the atom. You can see what kinds of light will the atom accept, and that's called the absorption spectrum.